All right, hello, my name is Areana George, and welcome to my presentation on the Fcc Atomic Structure. As we know, atoms are the building block of all materials, and for crystalline structures, atoms are stacked in a 2D array, such as these, like the square array where they're stacked directly on top and directly beside each other, or this close packed array where they're offset a little bit. And then these 2D structures are stacked on top of each other vertically. It creates a 3D crystal structure like this one. Materials are created by a collection of these crystals, and there are different types of crystal structures that depend on how the 2D arrays stack on top of each other. So today we'll be talking about one specific structure called FCC, or face-centered cubic structure. If you look at this picture of the FCC structure, you can get kind of a clue as to why it's called the face-centered cubic. There is an atom at the center of each cube face, so each side here, and we'll talk about that a little bit more later. So firstly, we should talk about the unit cell. A unit cell is the smallest repeating unit of a crystal structure. So once you have those 3D crystal structures we talked about earlier with the 2D structures stacked, then the smallest repeating unit will be this little piece here. And then this image on the right will show us a little bit more about what's going on in that unit cell. So we have an atom at each of the cube faces, and then an atom at each of the cube edges. Now, within the actual unit cell, it's only going to be 1/2 of the atoms that are at the cube face, and it's only going to be 1/8 of those atoms that are at the cube edges. And I can show a little bit better detail. So obviously that image before was a little simplified, so you could actually see what was going on, but they won't be this small. They'll actually be much tighter packed. So here's a unit cell of FCC structure, and we've got 1/2 of an atom at each of the faces. And then we've got 1/8 of an atom at each of the cube edges here. All right, so atomic packing is how tightly the atoms are packed together within a unit cell. The atomic packing factor is a value that helps us quantify how tight the atomic packing actually is. And it is going to be the volume of the atoms present in the unit cell divided by the total volume of the unit cell. So if we look at our model again, you can see there's a little bit of empty space in between the atoms in the unit cell, and we want to know basically within this cube how much of that space is atoms as opposed to being empty space. Okay, so as you can see with the FCC structure, it looks like a pretty tight fit, and let's see exactly how much it is. We can label each of the cube edge or cube sides as A, and because it's a cube, all sides will be the same length. And the total volume will be A cubed. However, we don't know exactly how much A is because of that gap. So this gap here would be unknown for the unit cell that we're looking at here. Okay, so we can use some trigonometry to actually help us figure out what the actual length of A is. Now, to do that, we first need to look at the close packed direction. And that will be the length of the unit cell where all of the atoms touch. And you can see with the close packed direction for FCC labeled on the face of the cube here. And that'll be where these atoms are touching at the cube face. And then if we look at our model from the top, we can see that that is the center of one cube to the edge, the center of one atom to the edge, the entire diameter of this hemisphere, and then the edge of another sphere to its center. So that'll be one radius, two radii, and one more, making it 4 times the radius. Okay, so now we know from trig that a right isosceles triangle, or a triangle with a right angle and 2 sides of equal length, will have an hypotenuse of square root of 2 times whatever that length is. So our length is a, and our hypotenuse hypotenuse is square root of 2 times a. And we also know that that is equal to 4r, and this gives us a little equation that we can use to relate the radius of the atoms to a. Now, the numerator of the equation is the number of atoms times the volume of the atom. So as we talked about before, the number of atoms in the unit cell, we can end up actually counting it. So we've got one hemisphere at each face, and that's half of a sphere at 6 faces, meaning 6 times 1/2 is 3, that's 3 atoms. And then we have 8 edges here, and they each have 1/8 of a sphere. So that'll be 1 atom. So altogether we have 4 atoms in the unit cell. And then we're going to multiply that by 4/3 pi r cubed in our equation here for the volume of a sphere, except we're going to replace r with what we found it to be equal to in terms of a. So that'll be square root of 2 times a over 4, and then we're going to cube all that. That'll be r cubed, just so we can get this equation on the same in terms of the same variable. Now, FCC structures have the highest possible packing of spheres with an APF of 74%. So most of this sphere, 74% of it, is actually atomic mass, and then the spaces here will be the other, like 26%. Okay, and some common types of metals that have FCC structures are aluminum, copper, gold, silver, also a certain type of iron. They are very commonly used due to some of their important characteristics. Some characteristics of these metals are that they are very strong, ductile, meaning they are bent or shaped easily without actually breaking. They have a high melting point, and they are tough, meaning that it requires more energy to break them. Hence their wide range of applications. Many of their other properties can depend on the elements that are involved. So what exactly the atoms are, the purity of those atoms involved, and temperature, etc. Thank you so much for listening, and a huge thanks to Dr. Pyatt for teaching us and giving us a great semester where we learned all this information and more. Here are a few references if you would like to learn more about this subject.